Thanks, Keith, for that introduction. And I'm really excited to be telling you all about our work on enabling practical and robust neural compression for video conferencing. So before I delve into the details of what neural compression looks like, let me give you all some context on what the traditional video conferencing pipeline looks like. So we have a sequence of camera frames that are read off at the sender side that we call target frames. These are then put through a video encoder that generate a sequence of encoded video packets that are then transmitted over the network. These are then received on the receiver side, decoded, and displayed as the decoded video. The amount of data transferred over the network is dictated by this target bitrate feedback that you get from the receiver to the sender. So the lower the target bitrate is, the sender compresses more aggressively and ends up sending less information over the network. But the more distorted the resulting video looks relative to the original frames that were read off at the sender side. So these codecs have been around for quite a while, but how well do they actually work in practice? To measure this, we ran this experiment where on the top graph, we supplied a time-varying target bitrate that starts out at about a megabit per second and then drops down to a few tens of kilobits per second. And in response to this target bitrate, we measured the achieved bitrate by the classical codec in the top graph. And on the bottom graph, we measure LPIPs, which is a learned perceptual quality metric that reflects how different the resulting decoded video looks relative to the original frames. LPIPs is a distance-based metric. Lower is better. And this experiment was at 1024 by 1024 resolution in 30 frames per second. So if you look at VP8, which is a widely supported codec in its Chromium settings, you'll notice that initially it responds quite well to the target bitrate, gradually matching it in terms of its achieved bitrate, and the LPIPs also worsens to reflect the fact that the video is compressed more and more. However, it saturates at about 550 kilobits per second. Nothing salient about this number. This is one particular experiment in a particular video. But the larger point here is that these classical codecs rely on search-based algorithms that look at every block of the current video frame and compare it to every other block of the previous frame. And these search-based techniques are fundamentally limited in real-time settings in how much they can be optimized or how much compression they can achieve. And this is consistent with the fact that most video conferencing applications recommend about 2 to 3 megabits per second minimum for reliable video calling. So this is the recommendation. Where does the reality stand in terms of global bandwidth speeds? So this is an infographic of broadband speeds across the world, with yellow regions denoting those areas that can only support a few megabits per second, with purple regions denoting those areas that have upwards of a few hundreds of megabits per second. Caveat that this is broadband speeds, and many of us often run video calls on cellular networks, which are far worse. But this already tells you that there are many people in regions of Africa and Asia that sit well outside the video conferencing ecosystem today because their broadband speeds simply cannot support one person in a household, much less an entire household. This also suggests a rather rosy picture for those living in North America and Europe. But our lived experience tells us otherwise. We're all familiar with some version of, can you see me now? Can you hear me now? I lost your video. And in fact, a widely conducted survey of North American users of video conferencing services resulted in about 30% of people saying that video quality-related issues was their biggest pain point when it came to virtual meetings. So you might ask, why is this the case if these regions can support such high broadband speeds? And that's because these disruptions are not really defined by the average broadband speed, but rather by these tail events. So we're talking 1 second of network congestion every few minutes. And it's really hard to solve these problems by simply adding capacity. There's so many things that can go wrong when two people are running a long-distance video call. And our expectations from video conferencing has only gone up over time with the emergence of 4K and virtual reality. So instead, we ask if we can dramatically reduce video conferencing bandwidth requirements so that we can bring more people into the ecosystem, as well as improve the experience for those of us already part of the system. At its highest level, Gemino does precisely this with its neural video conferencing solution, where we replace traditional signal processing with predictive modeling. The highest level idea here is that Gemino takes the same camera frames that are read at the sender, first puts it through a downsampling module that generates low-resolution target, which is then transmitted over the network. So with Gemino, we first put the target frames through a downsampler that generates a sequence of low-resolution versions of the same target that are then put through the video encoder to generate the encoded video packets. What's received on the receiver side is also low-resolution frames. So we first use a neural decoder that's aided by a high-resolution reference in order to produce the reconstruction at high resolution. Because we're sending low-resolution version of the same target frames, we can get away with much better bitrate savings, and the underlying codec is also able to operate a lot more smoothly. If I want you to take away one thing from this talk, it's captured in this video strip. The leftmost column shows you the ground truth. The middle two columns show you VP8 and VP9 at their respective lowest points. And the rightmost column shows you Gemino at 75 kilobits per second. I'm not here to try to convince you that Gemino is perfect at 75 kilobits per second, but rather that it is able to produce video that looks quite reasonable and something that can sustain a video call despite operating at 75 kilobits per second. This is qualitative. Quantitatively, on average, we're seeing about a 7 to 10x reduction in bitrate from VP8 with reasonable quality. And for the exact same visual quality, we're seeing a 2.2x and 5x reduction relative to VP9 and VP8. To give you a quick sense of where these bitrate savings are coming from in Gemino, on the left-hand side, I show you a 128 by 128 target at scale that represents something that is actually compressed and sent over the network in our system. And the right-hand side shows you, relative to the left-hand side, the 1024 by 1024 target that is actually displayed on the receiver side. And this gives you a quick sense of the extent of upsampling that we're doing. This is 8x in each dimension. So we're extrapolating 64 pixels of information from one pixel that's actually available. And it's this kind of extreme super resolution that really enables video conferencing at audio-like bitrates. At this point, you may wonder, how is this different from traditional super resolution? To show you this, to explain this part, I'm going to show you the exact same frame that I had in the previous slide on the left-hand side. And on the right-hand side, I blow up the 128 by 128 target to match the size of the 1024 by 1024 target. When I blow up the image, what I'm doing is a bicubic interpolation. But most learned approaches also have the same issues, wherein the high-frequency content, specifically on the top of the microphone, as well as the details of the hair, are entirely missed in this upsampled version. And this isn't surprising. This information is simply missing in the low-resolution version of the target. So there's no way any approach that's extrapolating from that will be able to fill that. So instead, we ask if we can recover this high-frequency information from a reference frame that's at high resolution and tells you exactly what this microphone head might look like or what the details of the hair look like. So it's with this insight that we designed Gemino, where we first initialize the receiver at the start of the call in all our experiments with encoded features that come from the high-resolution reference. On every single frame that's read off at the sender side, read off the camera at the sender side, we first downsample it to produce its low-resolution version. The low-resolution version is compressed and transmitted over the network. Once it's received on the receiver side, the receiver first runs a motion estimation module that tells it how it needs to warp or transform the features from the reference frame to the target pose. So you can think of this as if the reference is facing the right and the target is facing the left, the warping field tells the model to rotate all the features towards the left. So this gives you a sequence of high-resolution features to decode to produce the prediction. But in addition to this, we also add information or features directly coming from the low-resolution target in the decoding pipeline. So what results is a design with two pathways. One is the super-resolution pathway coming from features directly from the low-resolution target. But this is conditioned or aided on information coming from the other pathway that is provided by the high-resolution reference and warped to the target pose. So we call this design high-frequency conditional super resolution because it's super resolution conditioned on this high-frequency information from the reference frame. To evaluate Gemino, we built a system prototype atop WebRTC where we repurposed the existing video stream and turned it into a reference stream. You can think of this as used very sporadically, and it operates at full 1024 by 1024 resolution, but we only send reference frames if there's a huge change in background that necessitates that. In all our experiments, we use a single reference frame, which is the first frame of the call. On every single frame that's actually read from the camera, we first put it through a downsampling module and then send it on a per frame stream. This per frame stream is set up to be flexible to its input resolution, so it can operate at 128, 256, 512, or 1024. And it is coupled with a resolution-specific decoder on the receiver side that decodes and supplies the decoded frame along with the reference frame to the model for reconstruction. This per-frame stream is deliberately made flexible to its resolution because we use the same target bitrate feedback that comes from the receiver to the sender, and it uses this information to decide how much to compress the frame or what resolution to operate at. So if the target bitrate is lower and network conditions are bad, then it compresses very aggressively and switches over to a much lower resolution, say 128 by 128. But if the network conditions are good enough to send a higher resolution frame, it might as well send a 512 by 512 frame and get away with less upsampling and better quality video. In order to get the system actually working, we had a number of other optimizations that we had to do. I'll leave the details of this to the paper, but I'll briefly describe the most important ones. So these fall into two categories. One is model fidelity-related improvements. And here we design a new codec-in-the-loop training approach wherein we actually train the model with decoded frames that come out of the video codec at a particular resolution and target bitrate. So it learns to overcome the artifacts associated with the codec, particularly at lower bitrates. We also personalize the model in order to let it learn the specific features associated with a particular person. The other basket of optimizations fall under the computational overheads aspect. And here we use a new multi-scale architecture where we run different parts of the model at different resolutions. So for instance, we run the motion estimation module, which requires more coarse-grained information at lower resolutions so that we can save some of the compute associated with running convolutional operations at higher resolutions. We also use neural architecture search techniques in order to further optimize our model for inference. To evaluate Gemino, we curated a custom dataset consisting of 5 YouTube channels, 15 trained videos, and 5 test videos each. These were extensively pre-processed to crop 1024 by 1024 front-facing sections. We personalized these models for each celebrity and configuration and trained them with a number of standard losses. We evaluated this by measuring the PSNR structural similarity and learned perceptual quality metric. Most of these evaluations were run on A100 systems, but I'll briefly describe some numbers on other systems. So the first comparison I'll present is Gemino against traditional codecs. So here I present these rate distortion curves where the x-axis shows you the bit rate and the y-axis captures the distortion or how good the resulting frame looks relative to the original in terms of the SIM, PSNR, and LPIPS numbers. SIM and PSNR, higher is better, LPIPS, lower is better. So as I mentioned so far, VP8 saturates at about 550 kilobits per second. VP9, a newer generation version of VP8, is able to operate a little under 200 kilobits per second and gradually trades off video quality as it's compressed more and more. Gemino really extends the operating regime past VP9's operational point down to a few tens of kilobits per second, achieving better quality than VP9 at a particular bitrate, but also to get the exact same LPIPs. If you compare VP9, VP8, and Gemino, VP8 and VP9 require 5x and 2.2x of Gemino's bitrate for comparable reconstruction quality. This is the entire bitrate regime. By focusing on the sub 200 kilobits per second regime, here VP8 and VP9 don't really function. But to get a comparative set of data points, here we use the same downsampled low-resolution video compressed and provided to Gemino, but we upsample it using bicubic instead of Gemino. And here, once again, we see bicubic atop VP9 requires 2x of Gemino's bitrate to provide comparable reconstruction quality. To give you a quick visual sense, at 45 kilobits per second, bicubic's reconstruction has a number of artifacts on the face relative to the target, while Gemino has a much smoother reconstruction. So this compares Gemino to traditional codecs. I'll now present some comparisons to learned codecs. But before that, I want you to quickly recall that we have 2 pathways with Gemino's design. One that provides high-resolution features from a reference frame, and another that's super resolution-based. To compare to other learned approaches, I will compare with 2 classes of learned approaches, each of which use one of these pathways, but not both, to reinforce how important it is to use both. So the first class of approaches uses reference frames and warps those features, but doesn't use a low-resolution frame, but rather uses key points or facial landmarks that tell you where the eye, nose, and mouth are to capture the pose. Turns out the first-order motion model, one such approach, does quite a bit worse than Gemino, because these key points are fundamentally limited in how much information they can transmit. So as a visual example, here in the first row, when the reference and the target have large motion, the first-order motion model just produces a blob, whereas Gemino produces a much more accurate reconstruction. And if there are new parts in the target frame, such as a palm, then these first-order motion models cannot simply transmit that information using key points. And encoding and decoding features from the reference results in that palm entirely being missed in the reconstruction. The second class of learned approaches are content-adapted super-resolution approaches that simply upsample but without the reference frame. And here I show you a CDF across frames and videos comparing Gemino to such an approach. And Gemino consistently outperforms such a pure upsampling-based approach in its LPIPs. And visually, this manifests as missing high-frequency content on the microphone head, as I showed you before, which Gemino is able to leverage the high-resolution frame for. Lastly, I'll present some quick numbers on the speed of Gemino. So here, for context, real-time reconstruction is 33 milliseconds for 30 FPS. The first-order motion model on an older generation Titan X GPU requires about 190 milliseconds to reconstruct a single frame. The optimized version of Gemino is able to do the same reconstruction in 27 milliseconds, which is well under the real-time deadline. I started this talk with this bitrate adaptation graph, where I supplied a target bitrate that started at about a megabit per second and went down to a few tens of kilobits per second. VP8 saturated at about 550 kilobits per second and stopped responding to the target bitrate. In contrast, Gemino is able to respond to the target bitrate in the entire regime down to a few tens of kilobits per second. And the way it does this is, as the target bitrate is lowered, it switches over to a lower resolution and compresses that lower resolution video. So it switches from 1024 to 512, and then 512 to 256 when it can no longer support 512, and so on and so forth. And the LPIPs also shows a gradual degradation, because as you switch to lower resolution and perform more upsampling, the video gets more and more degraded. That brings me to the end of my talk, and thank you all for your time, and I'm happy to take any questions.